In today's video, I'm going to be going over fluid pressure using the Under Pressure simulation from PhET Interactive Simulations. Now, before we get started, please don't forget to subscribe to our channel, Step by Step Science. Get all of our excellent physics, chemistry, and math videos. When I look at our YouTube channels, I see that so many people who watch our videos have not subscribed. Please subscribe, support our channel, click the notifications bell so you don't miss anything, give us a thumbs up, leave us a nice positive comment, and don't forget to share this video. In addition to that, I have made a bunch of other teaching and learning materials which you can find at our Teachers Pay Teachers website, including a lab that goes with the Under Pressure simulation. All of our teachers' materials are available at our website. The link is in the description below. Now, as I said, we're going to be using the Under Pressure simulation from PhET Interactive Simulations. Here is their website. The Under Pressure simulation is an HTML5 simulation. It works very well, and you can run it on all of your computers, your Chromebooks, and all of your tablets. All right, so let's get started. Now, before we go on to the simulation, let's just go over a quick overview of what pressure is. Pressure is simply defined as the amount of force per unit of area. This is the equation that we use to calculate pressure. Pressure is equal to force per area, force divided by the area. And that means that the force is going to be measured in newtons, of course, and the area, you need to make sure that you have the area in meters squared, not centimeters squared like some problems will give you. You need to convert so you have meters squared. That means that the units for pressure are Newton per meter squared. Now, normally we don't say Newton per meter squared, we say Pascals, and that's named after Blaise Pascal. And the abbreviation for the Pascal is a capital P and then an A. And that means that 1 Pascal is equal to 1 Newton of force per each square meter of area. Pressure is a scalar quantity. You only need to give its magnitude. It's not a vector quantity, so you don't need a direction. It's a scalar quantity, magnitude only. Now, for the units for pressure, the most common unit is the Pascal, which we said is 1 Newton per meter squared. But you will also see some other units are common, such as 1 atmosphere. 1 atmosphere is the mean pressure at sea level. And 1 atmosphere is equal to 101,325 pascals, which you will sometimes see written as 1.01 times 10 to the 5th pascals. Commonly, it's given in kilos pascals because this is 101,000. So most commonly, you will see it written as 101.3 or 101.325 kilopascals. And that, in fact, is the unit that we'll be using mostly in this simulation. There are other units such as millimeters of mercury, and there are other units in the English system that 1 atmosphere is equal to 14.7 pounds per square inch. All right, but again, we'll be using metric units, and the metric unit is the Pascal, and we'll be talking in kilopascals. Now, let's talk about fluid pressure, because we're going to be talking about fluid pressure in the video and in the simulation. And remember that pressure is force per unit of area, and we're going to be talking about the force from a fluid, most often a liquid and most often water. There's a lot of water on the earth, so we often have problems where we talk about the pressure at depth below the surface of the water. For that, we can use this equation to calculate the pressure. Now, I made a video, which I can link to in the upper right-hand corner, of how we get from this equation and derive this equation. But this equation says that the pressure is equal to the density of the liquid times the acceleration due to gravity times the height below, or the depth. We often use an H, but really we mean the depth below the surface of the liquid. So this equation is the equation that we can use to calculate the pressure at a depth below a liquid. Now, in addition to the liquid, on Earth, we also have this thing called the atmosphere. And the atmosphere gives us additional pressure. So when you're underwater, you have the pressure from the water, but you also have the pressure from the atmosphere. So in order to get the total pressure, we're going to use this equation. And this equation simply says that the total pressure is equal to the pressure from the atmosphere. P0 is the pressure from the atmosphere. Sometimes you'll see a PA, or maybe you'll see something else, but we're going to use P0. So all we're going to do is we're going to add that to the pressure from the liquid. So the total pressure is simply the pressure from the atmosphere plus the pressure from the liquid. Okay, so that is the equation that we're going to use in this video when we talk about kilopascals. Now, remember that the pressure from the atmosphere is 1 atmosphere at sea level, and 1 atmosphere is 101.325 kilopascals. Okay, this again in the simulation is what we'll be using for atmospheric pressure in kilopascals. Okay, now we can go on and we're going to look at the first window from the simulation Under Pressure from PhET Interactive Simulations. When you open the Under Pressure simulation, this is what you will first see. There are 4 different windows for this simulation. This is the first window, this is the second window, this is the third window, and this is the fourth window. We are, of course, going to start with the first window. Now, there's some other features I'd like to point out. You can turn the ruler on or off. You can turn the grid for measuring depth on or off. You can leave the atmosphere on, or you can turn it off. I like to leave the atmosphere on because I think it's a little bit more realistic. You can have the measurements for units in metric system, which would be Pascals. You can have it as atmospheres, or you can use English units, which would be pounds per square inch. We will, of course, use it for metric. We can change the density of the fluid, which in this case is water, 1,000 kilograms per meter cubed. And then you could change gravity. We're here on Earth, and we're going to stay here on Earth for a little bit, so therefore we're going to leave gravity as 9.8 meters per second. That's the acceleration due to gravity. If I want to fill the tank all the way up, I can fill it up like that, and then of course if I want to drain it, I can pull on that valve and it drains it. Now I'm going to fill the tank all the way up, because in this screen, in this window, what we want to look at is what is the relationship between the pressure and the depth below the surface of the liquid, in this case water. Now I'm going to turn the grid on, and we want to ask ourselves, what's the relationship between pressure and depth? Now I can measure the pressure using one of the pressure gauges. There are actually 4 different pressure gauges, and I'm going to show you first as I bring this down right to 101.325 kilopascals. That is atmospheric pressure. I'm right at the surface. As we said earlier, 1 atmosphere is 101.325 kilopascals. That pressure at that location is just measuring the pressure from the atmosphere. You can see if I turn the atmosphere off, then it goes to 0. I'm not in the liquid at all. There's no liquid pressure from the water. Okay, I can turn that on, and now I get the total pressure, because now I put this down here, and now I'm getting the pressure from the liquid plus the pressure from the atmosphere. And if I put these gauges in here, as I said, there are 4 of them, so we might as well just use all 4. You can see as we increase the depth that we increase the pressure, and that tells us that the pressure and the depth are directly proportional, and you know that from the equation, because pressure is equal to the density of the liquid times the acceleration due to gravity times the height below the surface. And you can see that right there, that the pressure is directly related to, or directly proportional to, the depth below the surface. Now another thing we can do, which you can just show the same way but a little different, of course you're going to get the same results, is you can put one right in the middle there, and we're going to drain the tank and see what happens to the pressure as the surface of the water comes down. But once again, let's just check and show you we can turn the pressure from the atmosphere off. We turn the atmosphere off, and now we have 29 kilopascals approximately. That's without the atmosphere. Remember, atmosphere pressure is 101.3. So we turn the atmosphere on, you add those up, and you get about 130 kilopascals. Now, if I drain the tank, you can see as the depth decreases, the height decreases, then the pressure is also going to decrease. And that shows us once again that the pressure and the height are directly proportional. All right, if I drain that like that, then the pressure decreases, I can fill the tank up, and the pressure once again increases. Okay, so from that screen, you can investigate and you can see that the pressure and the depth are directly proportional. Okay, now we can go on and look at the second screen. Okay, here we are at window number 2. And in this window, we're going to look at the relationship between the shape of the container and the pressure at depth below the surface of the liquid. You can see here these 2 containers are connected to each other. It doesn't actually matter whether they're connected to each other, but you can see in this case we can drain and then we can fill up both containers at the same time. And we want to ask ourselves, if I go to a certain depth and I go to the same depth, will the pressure be the same? Now I'm going to turn the grid on, and we're going to look at 2 meters. Is the pressure here at 2 meters going to be the same as the pressure here, or is it going to be greater or less on one side or the other? You can see it looks like the volume of water above this point is less on this side than the volume of water above this point on this side. And you might think, well, there's more water up here, so therefore there's going to be more pressure. But if you think about the equation, the pressure is equal to the density times the acceleration due to gravity times the height. Then you will see if we bring a pressure gauge to 2 meters, and we bring another pressure gauge over here to 2 meters, you will see that we get the exact same pressure. Because the pressure is only dependent upon the density of the liquid, and we have water, has the same density on both sides. Only dependent upon the acceleration due to gravity. Well, these two are at the same place on Earth, so the acceleration due to gravity is the same. And it's only dependent upon the height. And you can see in both cases we're 2 meters below the surface of the liquid, and therefore we have the same pressure. You can measure also the same pressure here at 1 meter, and you see you get the same value. And you can also measure here at the bottom at 3 meters, and you see you get the same value for the pressure on both sides, just like that. And you can see if I put this back here at 2, and I put this back here at 2, even if I drain the water, okay? Even if I drain the water, the pressure decreases at the same rate, and the pressure always stays the same. Even if I increase the water, okay, and increase the depth, then we get the same pressure. So that shows you that the pressure at depth is not dependent upon the shape of the container. It's only dependent upon the density, the acceleration due to gravity, and the height below the surface of the liquid. All right, so that is screen number 2, and now we can go on to screen number 3. We are at screen number 3. And in screen number 3, we're going to look at a little bit more detail about what Pascal's principle or Pascal's law actually says. Okay, now I've already placed 4 different pressure gauges at different depths. As you can see, these two are reading the same pressure, so we know they're at the same depth below the surface. We can't change the volume of the water in this screen, but we're not going to need to do that. This one is at the greatest depth, it has the highest pressure. These two are at the same depth, they have the same pressure. This one is at the lowest depth, so it has the least pressure. And we want to see if we take one of these masses, we have two 250 kilogram masses, we have one 500 kilogram mass. And if I put this mass right here, that is going to add force over a certain area. So that's going to add pressure to this liquid. And we want to see how is that going to change the pressure at each of these depths. Is the pressure change going to be the same? Is it going to be greater at a greater depth and lower at a lower depth? Or maybe it's the other way around. So what we're going to do is we can see that each of these, I tried to put these at like whole numbers as close as I can. This is 123, this is 120, this is 120, and this is 103 approximately. Now I'm going to add the 500 kilogram mass to this column. This is the only place you can put it. You can't put it over here. And it only goes right here. And you can see that in all 4 cases, in this case, in this case, and this case, and over here, that the pressure increase is the same everywhere throughout that fluid. It doesn't matter at what depth. It doesn't matter the shape of the container. It doesn't matter whether you're close to the surface or at depth. You can see if I take it out, they all go back to where they were before. And you can see if I put this mass in here, that all of the pressures at each of those locations increases by about 0.8 kilopascals. That means that the pressure change that occurs here at this surface is transmitted equally throughout that container. And what Pascal's principle actually says, I'm just going to read you the definition. Pascal's principle states that a pressure change at any point in a confined, incompressible fluid. So water is incompressible, air is not, but water is in this case, that change is transmitted throughout the fluid such that the same change in pressure occurs everywhere. And we saw that. We take this out, the pressure goes down, we add this, and the pressure goes up the same at each location, and it increases by about 0.8 kilopascals. That law was established by the French mathematician Blaise Pascal in 1653, and then he published that in 1666. So that was a long time ago that Blaise Pascal was doing that work, and that is what is known as Pascal's principle. Okay, and that is what we can see from screen number 3. And now we can go on to the last window, and that is going to be window number 4. So here we are now at window number 4, and this is the mystery window because we have mystery fluid and mystery planet. And in this window, what we're going to do is we're going to use Pascal's principle, the equation for Pascal's principle, to find the density of fluid B from mystery fluid. And then we're going to switch to mystery fluid to mystery planet, and then we're going to find the acceleration due to gravity. We're going to find gravity on planet B. So we're going to start out by finding the mystery fluid. I'm going to fill this tank all the way up. All right, and we're going to leave the grid. We're going to turn the grid on. And you can see here, even though we have a mystery fluid, we're still on Earth, and the gravity is 9.8. So we're going to leave that like that. Okay, and what we're going to do now is we're going to go back to our presentation, and we're going to look at what we need to get to solve this problem, to find out the density of fluid B. Now we're going to use our equation from Pascal's principle, which says that the total pressure is equal to the atmospheric pressure plus the pressure from the fluid, which is density times G times H. Okay, we want to find the density, so we're going to solve this equation. For density, we're going to subtract atmospheric pressure from both sides, and then we're going to divide by GH, G times H, which gives us that the density of that fluid B is going to be equal to the total pressure minus the atmospheric pressure divided by G times H. Now we know the atmospheric pressure because we're on Earth, so we know the atmospheric pressure P0 is 101.325 kilopascals. We don't have the pressure at depth for that liquid, so we're going to go back to our simulation. We have the tank completely full, and I'm going to measure the pressure at, let's just say at 3 meters all the way down here at the bottom, just like that. Okay, now that's the pressure, and that is 125.983 kilopascals. Okay, so now we have everything we need, and we can go back to our presentation, and we have the pressure at depth. Now, when we measured it just there in the simulation, it said 125.983. When I prepared the presentation, and when I prepared the presentation and made the measurement, it was 981. But 981 and 983 are basically the same thing, so it's not going to matter. Because also, when we plug the values in now, for the total pressure, which is 126. I rounded this to save space here from 125.9 to 126 times 10 to the third, because this is kilopascals, and you got to put it in the base unit, which is Pascal. And then we're going to subtract from that atmospheric pressure, which is 101.3 times 10 to the third, again, kilopascals, times 101.3 times 10 to the 3 pascals. And then we're dividing by the acceleration, and then times the depth. And the depth is 3 meters, and you come up with the density of that fluid B, as 840 kilograms per meter cubed. Okay, so that's how you can find the density of the liquid using Pascal's principle. Now the next thing we're going to do, of course, as we said, we're going to find the acceleration due to gravity on planet B. And we're going to go back to our presentation. We'll get rid of this pressure meter for now, pressure gauge, and we're going to switch to mystery planet, and we're going to do mystery planet B, and I'm going to leave the liquid as with this density, which is water. Okay, we're on a different planet, but it's still water. If you change the density, it doesn't matter, because you'll get a higher density, of course, but then you'll get a higher total pressure. Okay, so let's just go back to our presentation and figure out what we need again. We're going to use the same equation. Of course, we're going to subtract the atmospheric pressure this time also, but instead of solving for density, we're going to solve for G, and that means G is the total pressure minus the atmospheric pressure divided by the density times H. Now, in this case, once again, we need the atmospheric pressure, but we're on a different planet, so we don't know what the atmospheric pressure is. It's not 101.3 kilopascals, all right? And we also need a pressure at depth. So we're going to go back to the presentation, and we're going to measure atmospheric pressure, and I'm going to measure atmospheric pressure like this. I'm going to measure atmospheric pressure right at the surface, and you can see if I go below, now it starts to increase. You can kind of see it increases rapidly. So I'm going to say that atmospheric pressure is 144.7 kilopascals, and then I'm going to measure the pressure at 2 meters. Once again, it doesn't matter whether you measure 1, 2, or 3, or some other depth. I'm going to measure at 2 meters, and at 2 meters, I get 173.018. Okay, so now we have our two pressures, And again, if you change the density, you're going to increase the density, but you'll also increase the pressure. So it doesn't matter whether you change the density, just make sure you get the correct measurements and leave everything else the same. So now we're going to go back, and we get the atmospheric pressure was 144.75. And once again, I have here 173.069. In the simulation, we just saw it was, I think, 173.018. But that's such a small difference because when we plug the values in, I'm going to round the total pressure, okay, which is the pressure at depth. That's the atmosphere and the liquid, or the fluid, the liquid water. And that's 173.1 times 10 to the third, because this is kilopascals and this has to be in pascals. Atmospheric pressure is 144.8 times 10 to the third pascals. Divide by the density of liquid times the depth, and you get that the acceleration due to gravity on planet B is 14.1 meters per second squared. Okay? So there you go. That's how you can use Pascal's principle to find the density of the liquid and the acceleration due to gravity on Mystery Planet B. Okay, so there you go. That is the whole video. That's the whole walkthrough of PhET Interactive Simulation Under Pressure. We showed you that. We showed you the relationship between pressure and depth. We showed you the relationship between pressure and the shape of the container. We showed you what Pascal's principle is. And then we used Pascal's principle to find the density and the acceleration for Mystery Planet B and fluid number B. So thank you so much for watching. I hope you found the video helpful. If you did, please don't forget to do all of the following 5 things. Okay, support our channel, Step by Step Science. Subscribe, click the notification bell so you don't miss anything. Give us a thumbs up, leave us a nice positive comment, and don't forget to share this video. Thank you so much for watching. We will see you in the next video.